Right, good evening and welcome to the BPhO round one training this evening. I think you've got me to start off. Hello, 207, excellent, more people, lots of hearts and emojis, the usual torrent. Good evening, everybody. If this is your first go at the Physics Olympiad, welcome. I'm Dr. Andrew French from Winchester College, and what we're going to be doing is going through some of the problems from the 2023 round one paper. And showing you guys how to go about solving those. So we're going to go super slow. We're going to really luxuriate in these problems and hope to give you some skills. So for maximum enjoyment, ideally with a friend, get a piece of paper, do some notes as we go. But you can also download all the questions in a sort of printable one question per page, easy use booklets. And that's what I would recommend you have a go at. When you're looking through these things. All right. So without further ado, unless there are any questions, hello to my amazing hosts. And if you have any difficulties or questions, put those in the chat, and our fantastic assistants from Oxford University will hopefully answer those. So here we go. Let's make a start, shall we? So here we go. We're going to have a look at this problem here. Which has some rather interesting things. So we're going to start with something which is more like radioactive decay and particle physics. So from the 2023 paper, this is question J. So what's going on? By the way, am I sharing okay? By the way, am I still sharing my screen? Have I not achieved that? Let's
not yet. No.
Ah, that's a good chance I checked that one. Otherwise, it would be. There we go. How about that? Is that working all right?
Yes. Yeah.
Fantastic, thank you. Right, so we've got a short pulse of 10 to the 8 neutrons is fired through a vacuum at a target. All right, so when we might see neutrons, I know maybe something like in a nuclear reactor, to cause the fission of something like uranium-235 or plutonium, and you can get neutron sources around, special sort of scientific institutions around the place. Now, this is really intriguing. So, according to this, I actually didn't know this until, well, basically now. Neutrons in the wild, as it were, has a half-life of 880 seconds. And that kind of begs a really interesting question, which I'm not going to attempt to answer tonight, but maybe some of you may think about this as a project or something to research, is that, well, how does that work inside the atom? These neutrons kind of refreshed. So, what does that mean in terms of stability? So there's an intriguing question to think about. All right, so we're going to take it as is. And so what we've got n naught neutrons. Here's our bunch of neutrons. All right, traveling at speed v. All right, and a bit later it says they're going at 2,200 meters per second. All right, and there we go. So there's 10 to the 8. So that's n0. And again, if this is the first time you've done this kind of stuff, I really thoroughly recommend going through these questions. They're all word questions, and labeling them, giving them some sort of algebraic reference as you go through, and then kind of putting that into a diagram. So we're going for 11 distance towards some sort of target. So here we go. That's going to be 11 meters. All right. So if we know the speed, we know how long that's going to take. And so what we've got is we've got a bunch of neutrons with n neutrons here, and these are still traveling at the speed v. All right. Okay. That's at our target. All right. So what's going on? Well, firstly, we might want to work out the time. So t is going to be 11 meters divided by 2,200 meters per second, which is whatever that is. And there we are. There's our time. And then we can think about the radioactive decay. So it's a half-life. So here's a really nice way of writing it. You might think of it with the natural exponent, but I personally recommend you do it like this. So what we've got is the number of neutrons versus time, okay? And we will have an exponential decay here, which looks like this. It's rather a thick pen. Let's try and change that. There we are. That's a bit better. Right, so here we go. Here's our exponential decay. And if that is n0, when it's n0 over 2, that's a half-life. So let's call that t half. And t half is 880. All right, so because it's an exponential decay, when we have n0 over 4, that's another half-life. So that's 2t half, etc. So a nice way of writing that curve is as follows. So basically, it's n is what we started with, and we're going to divide by 2 to the power of the number of half-lives. So t divided by t half. So So the exponent of 2 is the number of half-lives. Now that's often, I don't find you don't have that. That's not really how it's written in books, but I kind of think that makes a lot more sense to do it that way. And it doesn't matter when we take logarithms and that kind of thing. So that's how I'd recommend defining that curve is n0 divided by 2 to the power of the number of half-lives. So what have we got? So we can say therefore that n is 10 to the 8 divided by 2 to the power of, well, what is it? It's 11 over 2,200. That's the t. And we've got 880 seconds. So divide that by 880. So that's my number of neutrons. Now, what does the question ask? It says, how many neutrons will decay? So that is the number of neutrons left. So therefore, the number that decay, let's call that delta n, is going to be n0 minus n. All right. So this is a sneaky thing that you often find in these questions, is that rather than it's a sort of like the trap of just plugging it into a formula, all right, you won't get all the marks because it's actually the number that decays what you want. So you've got to really read the question here. And so now we've got that, well, let's just put all that all together. So what we've got, that means delta n, the number at decay. So n0 minus n0 divided by 2t over t half. So I'm sticking with algebra just for the moment. And that's going to be n0 and 1 minus our ratio. Let's just do it like that, shall we? So 2 to the minus t over t half. There we go. So that's what we've got. Now, if we put that all in together, what have we got? I make that about 394. So that's 10 to the 8 times 1 minus 2 to the minus, what have we got? So 11 over 2,200 times 880. So I make that about 394. So 390 to 2 significant figures. Why is it 2 SF? Well, it's quite hard to tell. Probably 11 meters. Yeah, I think that's 2 SF. So that's the worst precision. So I think that should be our answer. There we go. A nice quick question so radioactive decay. Nice. That's the first time you've met. If you're one of the sort of younger viewers today, welcome. Maybe that's something you haven't met before. But quite a lot of you in the sixth form, of course, will have met this for many years. So maybe something new, defining n versus t as the starting number divided by 2 to the power of the number of half-lives. And don't forget, we sometimes want the number at decay rather than the number that we have at the target. So this is a good example where, we can draw a little picture at the start to make sure that's nice and clear. All right, do we have any questions? That's our little warm-up. I think probably a nice, easy 4 marks, that one. Any questions there? Am I still broadcasting all right?
Yeah, all good. No questions so far.
Excellent. Right. Okay. So now there's a nice little mechanics one I thought we'd do, and then we'll do something a bit more involved. So there we go. All right. So the plan today, we're going to do a few questions and then stay with us. As usual, we're going to have something a bit extra, and we're going to again look at the cosmic ladder. So last week we looked at how to work out why the moon and the Earth are 60 Earth radii apart, and indeed why the Earth's radius is what it is and how to measure it. Today we're going to have a look at the distance from the Earth to the Sun, and maybe about the speed of light if we've got time. All right, so let's look at this one first. So mass m is suspended from a horizontal rod by 2 identical wires of negligible weight. Okay, and we've got some angles here. So this is a nice kind of equilibrium problem where the vector sum of the forces, and it might be a situation where we need to use moments, but I don't think so in this case. So let's make a free body diagram of this. So the first part, change an expression for t, the tension in each of the y in terms of m and g. So if you don't mind, I'm just going to redraw this diagram if that's all right. So what we'll do is we'll have, here's our mass. All right. So the angles, if you think about it, if that angle there is 30, if we kind of divide those, that's also going to be 30. That also is 30 degrees. So one of the first things you can do with mechanics problems is do a bit of geometry. So a free body diagram is what we want. And we've got our wires here carrying tension T. And we've got our weight mg here. Here we go, mg. And these angles are 30 degrees. There's 30 degrees. There's 30 degrees. Excellent. We've got G acting down here. And it asks us to do this, but let's just leave it like that for the moment. And there's our mass M. All right. And we want this, and the question's leading us to something algebraic. All right. We're only given the angles. Everything else is in terms of a parameter. Excellent stuff. So let's have a think. So what we're going to do, this is part I. So it's a free body vector diagram. So in equilibrium, the vector sum force is 0. So what we've got is a free body, i.e. force, vector diagram. Okay, so a nice thing, if there are only 3 objects, is a triangular forces. But of course, there might be more than 3 forces. So, I'm not. I think we should sort of be a bit more general than drawing triangles. But if you want to draw a triangle, sometimes that gives you a really, really good answer. I have a lovely problem involving a drawbridge, where actually the drawing of the triangle is a much quicker way of doing it than doing Newton 2. However, in this case, it's a bit of a moot point. So, if in equilibrium, the vector sum of force is 0. So what we can look at is in the x and the y direction. So in the x direction, we just got t sine 30 in both sense. So if we resolve vertically, what we've got is we've got mg, the weight downstairs, going downwards, must be t cos 30. Make sure that 30 degrees is actually the angle we've got there. Let's make that a bit bigger. There you go. So that angle there is 30. Oops, my pen has become a crayon-like large. Let's go for, there we go, marvelous, 30 degrees. And so what we'll do, there we are, is we'll resolve that. So we've got 2t cos 30, and that's going to be our balance. Okay, so that's our physics done. And we're asked to find out expression for t. Brilliant. So using our special triangle, we should always try this. We could just stick it into a calculator, but hopefully I'm sure you'll agree that that is a half. And that's √3 on 2. And that's a nice thing to memorize. If you're new, or I've not seen this before, the best way of proving that, all right, is to reflect it as if it was like in a mirror or on water or something like that. And that must be half because it's a equilateral triangle. And then you can use Pythagoras to find out √3 on 2. So 1 squared is a half squared plus √3 on 2 all squared. Yeah, so that's going to be 1 plus 3 over 4, which is 1. Okay, so cos 30 is √3 on 2. So therefore, what have we got? We've got mg is 2t √3 on 2. So therefore, our tension is going to be, so we've got our 2's cancel. So we've got mg over √3. That's what I got last time. Good. There we are. All right, so that's the first bit done. Now, the wire BC is cut. Oh no. The same is the tension of the wire AC, TAC, all right, will change as the system is down motion. So if that wire is cut, what shape is the motion going to be? Stick it in the chat, please.
Yeah, we're getting circular pendulum.
Yeah, good, because we're going to assume it's under tension, right? So in principle, you could like a thing like a conker, you could get some sort of flex, but we're assuming the tension hasn't gone to 0. So that means that that wire is taut, and we're going to get a vertical circle. So I've said at the instance, right, BC is cut. Right, T is bigger than 0, so motion will be a vertical circle of radius r. Right, what's r? Well, it's all been defined already. Not yet. So we're going to need to work that out. So let's call that r here. Let's define it, okay? And hopefully we won't need that in our final expression. So there we go. Sometimes you need to create something. So let's just redraw our vector diagram, all right? So what do we got? Here's our vertical circle. So there we are. I think I've just done it this way around just for fun. All right, so here's our mass. All right, that's r. Okay, and let's have, let's change color for our forces. Let's go for green, shall we? So what we've got, there's our tension. That's TAC. And we've got our weight here, mg. And let's just say that's the angle that starts off at 30 degrees. There we are. That's 30 degrees. And there we go. There's mg. And right, let's call that angle theta there. All right, and that must be 30 degrees. Let's call that theta, shall we? So we can talk about sort of like tangentially and radially here, what the forces are going to be. So this is all about circular motion. And what's quite a nice idea to talk about a radial unit vector. It's not entirely necessary for the solving of the question, but there we go. It's so these are what I've just defined is theta and r hat are unit vectors. And basically, they define the radial and the tangential direction. They're unit vectors, which means the magnitude of those things is 1. So they're there to kind of like define the direction of what's going on. All right. Right. So what we can say is we can do Newton 2. And let's go for radially and tangentially. And probably one of those is going to give us what we need. Now, this is going to start to move now. Let's call that velocity v. So that's the initial angle, but that angle is going to change. So, so at t equals 0, theta equals 30 degrees. All right, so that's the idea. And if I can use maybe a different color, that's going to form a sort of arc like that. All right, as it sort of swings. Right, so radially, what we're going to do, so mass times acceleration is vector sum of force. That's Newton's second law. Okay, can I just check, am I broadcasting all right still?
Yeah, all good.
Excellent, fantastic. So what we got? So radially, well, maybe we can ask this one. So can you pop in the chat if we've got we've got circular motion, what is the radial mass times acceleration? So what would be radially inwards? What would be our what's our acceleration? What's the formula in terms of velocity and our radius?
Okay, we got mv squared over r, we got v squared over r.
Very good. Excellent. So there we go. So mv squared over r. So we'll go for radially inwards, so the opposite of the r hat direction. All right, because obviously you don't want to burden our workings with too much notation. So that's our mass times acceleration. V squared over r is our magic formula for a centripetal acceleration towards the center of a circle. So even if we're going at constant speed, which we won't in this case, all right, we are changing our velocity all the time. So we must be accelerating. Right, so what is that going to equal? Well, we need our vector sum of force. So that's going to be TAC minus mg cos theta. All right, okay. Yes, I think that's okay. And there we go. Just check I've got my things the right way round. I think that's okay. And then, so tangentially, we've also got, so mass times the rate of change of angle. So basically, it will be dv by dt. And this bit here, so v is going to be the rate of change of arc, so r d theta by dt. That's going to be our velocity, because it's always tangential. So this bit here is going to be the angular acceleration times the radius. All right, so that is going to be mr theta double dot. And theta double dot, if you've not seen that notation before, is the second derivative of our second time derivative of our angle. And that is going to be mg sine theta. But obviously our angle is going this way. So, oops, wrong color. There we go, let's go for green. Theta is going that way, so we need a minus sign here. So mg sine theta, all right? And that will give us a sort of pendulum motion, sort of a simple harmonic motion for small angles, because you've got an angular acceleration. So if I just sort of write this, this is moving away from what the question asks here. Our mass is stable, so theta double dot, the angular acceleration is minus g over r sine theta. And if theta is small in radians, what we've got, that means theta double dot is approximately minus g over r theta. That's an equation of simple harmonic motion, where your acceleration is proportional to minus your displacement. Displacement in this case is your angle. So that's the sort of thing that gives us a kind of sinusoidal dependence on angle, which we could draw something like this. So there's theta naught, 30 degrees. And there's time, and we'll have something which looks like this. That's the solution of this equation. However, that's not what we want. All right. So what we want is we want the first bit. So let's go back to our question. What does it ask for? It's not the tension at all times. It's the biggest tension, I think. So let's go back to our question. It says the YBC is now cut at the same instant. The tension of the wire is this one. Right. And it will change what's now in motion. What's the ratio TAC to T? So this is the instant the wire is cut, right? So there we are. So let's have a look at this. So I'm just going to make that a bit bigger. I just want to check I've got a nice, let's go up here. So what we've got, let's just rewrite that. So what we've got mv squared on r is equal to mg cos theta minus, I've got this right way around, other way around, sorry, minus mg cos theta plus TAC. And so when it's cut, so let's just draw a picture. So there we go. That angle there is 30 degrees. All right, there's our mass. And what we've got, there's our tension, TAC. There's our weight. So at the instant it's cut, it hasn't started moving yet. So at the point of cutting, what can we say about the angles? Well, theta is 30 degrees. We've got V equals 0 because it hasn't moved yet. So therefore, we can work out the tension easily. So what we got, so therefore, so TAC is going to be mg cos theta. And theta is 30, so that's cos of 30, which is root 3 on 2. So that's going to be mg root 3 on 2. Okay, so we've got TAC is root 3 on 2 mg. And beforehand, so since, let's make that a bit bigger. So the first part of the question, we had T is mg on root 3. That's to balance things. So therefore, since our original tension is the weight on root 3, therefore TAC over T is going to be mg root 3 on 2 divided by root 3. Our root 3's cancel, and that's going to be, oh, hang on a minute, what have I done here? Nope, sorry. Apologies, not quite. So T is mg, there we go, on root 3. There we go. So our mg's cancel, which is nice. And what we're left with is root 3 over 1 over root 3. So that's 3 over 2. There we go. So we've got a kind of 50%, no, not quite 50% boost. We've got a bit more than that. We've got, yeah, oh, no, that's fine. Yeah, so 1.5. There we are. So we've got a 50% boost. All right. I hope that was fun. Oh, there we go. My computer's playing up a little bit. There we go. So in summary, this is a lovely question about equilibrium and vector sum of forces, a free body diagram. There you go, free body diagram. Let's put that over there. All right, and why you should draw them. Sometimes it's a triangle. Our special triangle, make sure you use those because, you know, the maths gets not nicer rather than sticking into a calculator. And all you really need to know is 30, 60, 90 triangles and 45, 45, 90 triangles. The ones that are, what, 36, 54, that's quite nice too, but that's involving pentagons. These are the ones to commit to memory. And then we've got a bit of circular motion. And most of the questions you'll come across, it's the radial part that is going to be interesting. So swinging conkers, that kind of stuff. You know, sort of circular motion where the radius is a constant. There's loads of problems like this, and this is how you do it. So any questions on what we have done or any kind of paradigm that's introduced? Hopefully that's clear. Any questions?
We're answering as we go.
Fantastic. Excellent, guys. Right. I think we're going to go and step things up a little bit. And I'm going to go and do the penultimate question, which is R, which when I had a look at this, so I think these are all amazing questions, don't get me wrong, but some of them are really, really good. And I have a sort of smiley face, which I put on the really, really good questions. So whoever wrote this, has got my respect. So this is good. And it's another buoyancy question. So if you came last week, and you had the sort of big ball. So I'm going to scroll a bit to the end. So, so that upsets your eyes. Look away now. There we go. Here we are. So we've got a uniform rod of length 2A, partly immersed in a liquid, being supported by a string fastened to one of its ends. The other end of the string is attached to a fixed point, as in figure 8. So yes, I'm very glad they've given you a picture here. So you've got basically this rod, and it sort of sticks. It's like a kind of straw. It's in a liquid. We're not told the density of the liquid, but we're told the density is 4/3 times that of the rod. Interesting. Okay, and all we know is its lengths. So let's put some geometry on this. Let's see if we can figure it out. All right. So firstly, let's just have a look. So let's call the distance that it's submerged. Let's maybe label some points. So I call that sort of A here. We'll call that B here. And we'll call that C is the point that's in the middle, something like that. All right, so let's dimension this. And I'm going to call that distance X. So this is a kind of question where you just need to invent a whole bunch of parameters that may or may not be useful. And that's how I think we should do it. So there we go. And it's 2A. So that distance there to B is going to be 2A minus X. Right, what else do we know? Let's go and put some forces on this. So we've got 3 forces here. We've got our tension in the string. All right, we've got the weight. Now that's going to act halfway. So that may not be at point C. As it turns out, that I think is the... No, that's not quite the case. But I think we might get a nice result here. But in general, that's not the case. So we need to kind of go halfway, and we'll put the weight, sort of roughly speaking, at the halfway point. There you go. So there's W, the weight, the mass times the strength of gravity. We've also got the upthrust as well, which let's have a think. So that may not also be in that position. So yes, I would suggest what we're told here. Yes, here we go. So the weight of fluid displaced is where that's going to act. And I think I'm just doing a little check of my notes here. Yeah, well, that's going to have to sort of go up somewhere. All right. So I will put that here. All right. So here's my upthrust. I just think it's out at point C. I don't think it is. There we are. Right. Okay. So let's put. Oh no. The upthrust, of course, must be where it's acting there. So there we go. I'm going to put my upthrust there. All right. So there we are. That's going to be my upthrust. Oops. That's going to be acting this way. All right. Let's have that there. U. Just looking at my diagram, I've got it at some other point, but I don't think that's. I think that's where it should be. All right. Okay. I think that's all good. And let's have some angles here now. Let's have. So that angle is theta. Then this is going to be theta as well. All right. I think we've got everything. That's density rho. And yeah, I think we've got gravity acting on this system. So I think that's all the parameters we need. Let's go and label stuff, shall we? So let's upthrust. U is upthrust, which is by Archimedes' principle equals the weight of fluid displaced. All right. So what we want, we've got W is the weight of the rod. And there we go. All right, I think that's all it. I don't think it's asked her to do any other things. So let's see, we can work a few things out. Right, well, we might need to work out something about the rod itself. We know its length, so we might need to work out its cross-section. So let's go and do that. So let's have our rod. Let's assume it's like a circular cross-section. Let's call that A. And that is 2A. All right, that's its length. So it's now we're told... sorry, no, rho is not the liquid. That's going to be rho. Let's call that times alpha, which I'm going to talk about. So let's go to rho alpha. There we are. So the density of the liquid is a factor of 4/3 times that of the rod. All right. So if that density is rho, all right, then the mass of the rod. So M is going to be so A times 2A. All right, that's the volume of my rod times the density. So therefore, the weight is going to be 2A rho AG. All right, so that's my formula for that. Okay, that's the weight of my rod. What about the upthrust? Well, that's going to be the rate of fluid displaced. So it's going to be, well, what's length x is in it. All right. So if I just draw a little picture here, so this is the bit that's submerged. Let's go for that in blue, shall we? All right. So there we go. There's my submerged bit. That's the same cross section. This bit is x now. That's in the water. All right. It's out of the water, beyond it. So there's my water level. Okay, so what's my upthrust going to be? Well, U is going to be the volume that's displaced. So that's going to be x times A. It's going to be times the density of the liquid, which is rho alpha. That's the mass of water displaced, and then times G. I think I've got that right. Yes, that's okay. Cool. Now I've used this alpha, right, because it might be fun to sort of do this slightly more generally. I think if you're doing this at speed, just put the numbers in. Hopefully someone set the question up so the numbers are quite nice. But we could do this in more general terms, I think. All right, so we can talk about the fluid being some factor times the density of my my rod. So there we go. So that's the upthrust. We've got the weight, and now we could just do sort of Newton 2 or perhaps moments. So I'm just having a little look at my diagram here. I think that's okay. Yes. So upthrust, it must be in the middle. Okay, so that's where things are pushing. All right. Okay. So let's do Newton 2 using these things. And what we want to find is sort of the ratio of x to 2a really. But we don't really need to know what t is yet. It's the fraction of the rod's length that's submerged is what we want. So x over 2a. So that's what we want. What's our goal? Sometimes it's worth just writing down what that is. What's our goal? We want x over 2a. All right. Obviously, we had to define what x is for that to make sense. And that's what makes these questions a little bit harder because you've got to kind of create your structure. I think before we go on, actually, are there any questions about what I've set up before we come and solve this?
There have been a few questions about whether point C is the center of the rod, where the upthrust is acting, or where the liquid is.
Right. Yeah. So what I've so basically what I said, the weight is definitely at the center, is acting through the center of the rod. So I'm trying to do my best there. So point C may not be the center of the rod. Okay. So the weight definitely acts. So if I kind of maybe put some extra dimensions on this one. So the weight of the rod is definitely acting at the center. We're assuming it's a uniform rod, right? So that's going to be A, and that bit there is going to be A. There we go. So if you maybe use a different color, but where the upthrust acts, I think that's I think point C should really be where because if you think about it, everything's sort of pushing up. So I think that should be there. I'm just checking if I've got no. That's exactly. Hang on a minute. No, it shouldn't be. I've put the view in the wrong place. So I'm glad whoever questioned that. So if you think about it, it should be in the middle of the bit that's displaced there. So U really should be here. There you go. That's better. All right. So let's have a look. Let's use a different color. Right. There we are. So there are brownie points for then whoever raised that. Okay. There we go. So that is going to be x over 2. All right, I think that makes much more sense now. So the bit that's underwater, the upthrust is going to be in the middle of that. Okay. All right. Okay. So this is going to be a moments question. So assuming it's all in equilibrium, right? So in equilibrium, the turning moments, the force times perpendicular from the pivot, it doesn't matter where you take that pivot. All right. The turning moments are always going to be summing to 0. So I think that's going to be a better way of doing it than looking at forces. All right, because remember, we don't really care about T. So I suggest what we do is we take moments about point B. All right, so let's just write that down. So since we don't care at the moment about T, therefore take moments. Okay, and I like to talk about the direction, so that's positive. All right, so it's a sort of clockwise moments about B. All right, remember it doesn't matter where we take moments because it's in equilibrium. So we're going to assume in equilibrium. So these kind of questions, you want to be really spend about a good amount of your time setting up the diagram, and then your moments calculation, you can look at it. So let's have a look. So I always take a lot of time doing this because we want to make sure we've got the right direction. So let's now take moments about B. So it's an equilibrium. So therefore 0 is going to be what? So what we've got the weight and the upthrust. There are, we want to take moments about from them about B. Now let's just have a look at our angles here. So angle theta, our angle of this, whoops, let's go for that one. So that must also be theta. I don't know why that's not red. Let's try that. Yes, that's red. There we are. So that's now theta. So what we got, so when you're taking moments, you can either do the force times the perpendicular distance, or resolve the force so it's perpendicular to the distance from where the force acts to the pivot. That's a lot of words. So let's go and write it out in maths and see how it works with the picture. So what I suggest is it's clockwise moments. So what we've got U, and I think we do need a little angle here as well. So that angle there, I just make that nice and red again. There we go. Right, so that angle there is also theta. All right. I hope that's not too difficult to see because the whole thing's been tilted by theta. So the angle sort of like from the sort of perpendicular is also theta. So what we've got, so U cos theta, all right, is going to be our clockwise turning moment times, well, we'll work at that in a minute. So U cos theta, that's the resolved part of the upthrust perpendicular to our rod. And we're going to multiply that by the distance of where U acts. So that's going to be 2a minus x over 2. All right, so that's going to be 2a minus x over 2. Yeah, we are. So that's the distance. Okay, so 2a minus x over 2 is the distance where my upthrust, if I can show that on a little, there we go. So this one here, that distance from there to there is 2a minus x over 2. All right, so that's my clockwise turning moment. What's going to be my anti-clockwise turning moment? Well, that's due to the weight, and that's going to be W also cos theta. And we're going to multiply that by 2a minus x. All right, because that's where the weight acts. All right, remember the, just check I've got my thing right, 2a minus x. Yes, I think that's okay. Yes, that's okay. Yep, that's all right, I think, because that's that point. Let me just check. I'm I'm just checking my notes if I've got that right. So where our weight is acting, that's in the middle there. I think that's okay. Yes, I think I've got that right. I'm just thinking that should be A away, should it not, from this one? Ooh, I hope I've not made a mistake here. I'm just double checking. Ha. So upthrust to express halfway along submerged rod. Yes, I believe that one. And our weight is, where is that acting? That should be A away. Oh dear, I made an error here. Right. Okay, I might just have to kind of busk this. That's interesting. So my notes, I've got 2a minus x to be where that's putting it. That would imply the weight's acting at point C, which is not quite correct. So I think, have I made an error here? Apologies for this one. I just double check my answers. Oh well, I think I'm just going to go for it. If I get something weird and wrong, we've got a self-cancelling error. So I think the weight needs to act in the middle of the rod. There we go. So I think that's going to be W cos theta times A. All right. Does anyone in the chat disagree with me? What do we reckon?
People agree with you.
Fantastic. Right. Okay. So there we are. So if you've been looking at my solutions, I'm going to write an errata here. Right. Okay. Well, that makes things a lot easier. So what we can do, rather than having to solve a nasty quadratic, we can find that immediately. All right. So we can relate the upthrust to that one. So let's just go and put all that stuff in there. So what have we got? Let's just put that. Let's do this here. So what have we got? Let's put it all together. So the cos thetas cancel. So what have we got? We've got, let's put it all to one side. So WA equals U 2a minus x over 2. And I think that's all good, isn't it? Yep, I think that's all good. I don't think we have an x on that at all. So that's nice and linear now. So let's now substitute for all our other bits. So what have we got? We've got xa rho alpha g. So x a rho alpha g, that's our weight, times a. All right, and we've got u. Oh, hang on a minute. I'm being very silly here. Sorry, chaps. Ladies and gentlemen, I've put the wrong way around. So what we've got is w first. So we've got 2a rho ag. That's w times by a. And then u is x a rho alpha g. There we go. That's going to be my u. All right. And then that's going to be multiplied by 2a minus x over 2. There we go. Right. Perfect. So let's see if we can put that together. What we're trying to find, we are trying to find the fraction that, so x over 2a. So we need to solve this for x. Well, that's all right. We do have a quadratic, just not quite the quadratic that I thought we'd had before. Right, what can we cancel first? So let's get rid of the a's. Let's get rid of the rows. That's all good. Let's get rid of the g's. And I think that is it. Right, brilliant. Right, let's go for it. So what have we got? We've got 2a squared equals, and we've got 2ax and minus x squared on 2. There we go. So we do have a quadratic to solve, so it's not as quite as straightforward as I thought and we might go for, because our upthrust and our weight also involve, well, our upthrust does involve x. All right, okay, so let's have a look. What do we want to find? We want to find x over 2a. So let's solve this quadratic. So x squared on 2, let's put it all the other side. We've got minus 2ax plus 2a squared is 0. Let's just multiply everything by 2. So we've got x squared minus 4ax plus 4a squared. And now we can complete the square or use the quadratic formula. So what have we got? So we've got x minus 2a all squared minus 4a squared. And that's quite nice, isn't it? So there we are, plus 4a squared equals 0. Well, that's rather lovely, isn't it? So therefore, x must be indeed 2a. That's pretty good. Or have I messed up here? Don't think I have.
I think you're missing an alpha.
Oh, I am missing an alpha. Thank you very much indeed. There we go. Ah, there it is. Right. I thought something was wrong here. There we go. Brilliant. There we go. Gremlins had to happen. Let's start again, shall we? So what we got? Let's do. So I'm going to change colours. That we are. That will make me feel better. So 2a squared. What have we got? We got x alpha. So 2a x alpha. There we go. Thank you very much, Sophie. X alpha, and then we've got minus x squared alpha over 2. There we go. Right. So let's multiply. Let's put this all to one side. So we've got x squared alpha on 2. We've got minus 2a alpha x. Make sure my alphas and my x look different. All right, plus 2a squared equals 0. There we go. So now I'm going to multiply by 2 and divide by alpha. So I've got x squared. So as 4ax. There we go. So multiply by 2, divide by alpha. And then this one, I need to multiply by 2. So 4a squared over alpha. There we go. That's way better. So now let's complete the square. So x minus 2a all squared minus 4a squared. And then I've got 4a squared divided by alpha is 0. Beautiful. So x minus 2a all squared. And what I need to do, put my 4a's on the other side. Okay, if I do this bad, it'll be 4a requiem. Get it? Ah, oh, sorry. And then wait, what we got? We got 1 over alpha here. There we are. That's all good. So let's go and sort of square root those. So x minus x equals, and we've got 2a, right? And then we've got plus or minus 2a, and then square root 1 minus 1 over alpha. There you go. Brilliant. So there we are. So what we want is x over 2a. So x over 2a is going to be 1 plus or minus this lot here, 1 minus 1 over alpha. And let's just check, do we need both roots? So we could do, so x over 2a. Well, let's have a look, possibly. Let's go and have a look. It's got to be, so I think one of them is going to give us more than 1, isn't it? So yeah, so x has got to be, yes, x over 2a cannot be bigger than 1, all right? Because that would mean, where our point C is, where the submerging point is going to be on the rod. So that's not allowed. So you must take the negative root. So since, right, x over 2a must be less than 1, that means x over 2a must be equals 1 minus the square root of 1 minus 1 over alpha. There you go. So that's slightly different to my previous result, which is, I think, a nicer one. So let's pop in 4/3 and see if that gives us a nice number. So if alpha equals 4/3, we're doing for time, right, x over 2a is going to be 1 minus the square root of 1 minus 4/3. Hang on a minute. Oh, no, it's 1 over alpha. 1 minus 3/4. There we go. Okay, so that's going to be 1/4. So equals 1 minus the square root of 1/4, which is 1 minus 1/2, which is 1/2. So there we go. So therefore x is going to be 2a over 2, which is a. So in this nice situation, the point C is indeed the middle of the rod, but that's not true if alpha was not 4/3. Right, so this is the nice situation. So if alpha equals 4/3, so therefore the liquid density, is that a bit bigger? All right, density, whoops, some sort of strange screen problem there. There you go. So rho equals equals 4/3 rho. Right, this means that the submerged point is literally the middle of the rod. There you go. There you go. Of the rod. There you go. There we are. There we are. You watched me make a mistake, but that's good. It's all how we get away from this. And if we get to an answer which you think, hang on a minute, something's wrong here. So I had x minus 2a all squared is equal to 0. So that's a bad smell. So the idea, go back and see where your error is. In my case, I've forgotten the alpha. There we go. So hopefully that's nice and clear. Did we ask to do anything else? Oh, the tension in the string. Well, that's quite easy. That's just W minus U. All right. So that's going to be, if you think about everything is in all one direction. So I'm just going to put that on here to finish things off. So T is going to be the weight. Well, let's do it in equilibrium. So 0 is going to be T plus the upthrust minus the weight, because they're all vertical. And so therefore, my tension is going to be the weight minus the upthrust. Now let's use our formula here. So our weight is 2a rho ag. And what we want to do is minus our upthrust. So x a rho alpha g. And I think we just want a formula for it. So I think, are we given all of those? I don't think we are. Let's just double check what my calculations were. Oh, yeah, it's in terms of the weight, isn't it? All right. Well, there we are. So what we can do, so if we sort of work that through, what do we got? We've got rho ag little a, and we've got 2 minus x here. X alpha is in our brackets. Okay, so if we divide it by the weight, so we can say that T divided by the weight, what's that going to be? Well, if we do, that's going to be rho AGA 2 minus X alpha divided by 2A rho AG. So there's the weight here. Let's just cancel a few things. We've got A cancels, A, G cancels, A rho. All right, and all we've got, I just changed color, is we've got 2 minus X alpha over, A goes as well, over 2. That's going to be 1 minus X alpha on, ooh, hang on a minute. I've got an A problem here. Let me just double check. Yeah, there we are. I factorized something wrong here. There should be an A there because I factored that out from this one. So there we go. All right. So what we've got is we've got 1 minus x alpha on 2a, I think it is. Yeah, that's going to be my fraction. So if I basically put that in, I think we should get a third or something like this. So therefore, so the tension divided by the weight is going to be 1 minus. So x over 2a is going to be, what have we tied to? That's going to be, so x is a basically. So if x equals a, we've got a times 4/3 over 2a. So that's going to be, the a's cancel. So we've got 1 minus 2/3, which is equal to a third. So there we go. So the tension is a third of the weight. There we go. So pretty cool question. We're just doing mechanics, really. We're using moments carefully. But the kind of fun bit is we're using things like upthrust as well. So yeah, that took a little longer than I expected. So sorry about that. Any questions? And I think then we'll go have a look at one of our cosmic ladder things. Oh, is your broadcasting?
Yeah, I think we're good with questions. I think we're answering.
Okay. Fantastic.
move on.
So here we go. So we're going to look at the cosmic ladder. That will load up, and there we go. So last time, what we did is we had the calculation of the distance to the moon of the Earth. So if you know the Earth radii, which is about 6,378 kilometers, the idea is that how you can work out the moon Earth distance to be about 60 Earth radii. And what we did last time is we saw if during a lunar eclipse, so if you have a look at this diagram here, what we've got is we've got the moon sort of going into the shadow of the Earth, and it travels an arc length of 2 Earth radii. And if you time that amount of time, it's about 208 minutes. So P1 to U4. So P1 is when it's just about going into the shadow, and U4 when it just kind of comes just about to come out of the shadow here. So and that's about 208 minutes. And if you work out that as a fraction of your orbital period, T, which is 27.3 days, so 27.3 times 24 hours. So that time fraction should be the same as the fraction of that arc, which is approximately 2 Earth radii, to 2 pi r. All right. So if you work that out, so delta T of the big T, that time ratio is about 1 in 189. And so what you've got is that ratio 2 pi r theta, right? So 2 r Earth, that distance over 2 pi r. That's the ratio of the radius of the Earth to pi times the distance from the Earth to the moon. And so if you equate those things, if you know what the Earth radius is, you can find the distance to the moon. So that is 189 Earth radii over pi, which is about 60. Okay, so 384,400 kilometers. So you can get that from just timings and measuring the radius of the Earth. So you can also use the same kind of argument to work out the radius of the moon. So we did that again, and just look at the time it takes for the moon to come in and out of the shadow. And basically it's the same calculation, but in this case, the distance that we travel, the arc, is going to be 2 moon radii. And that gives your moon radius as about 27% of the radius of the Earth. So this is the sort of cool stuff that the ancient Greeks were able to do. So can we do something similar to find out the sun Earth distance, which is much further, an astronomical unit? So there we go. So there we are. This is what Aristarchus of Samos, I don't know if that's what he actually looked like, but there's a statue of him wearing a toga there. And it's about, well, it's a large one, actually. It's about 23,386 Earth radii. So how do we work this out? So this is a really clever argument. And basically, if you have a look at the picture, this is what he did. So you take a new moon. So the sort of sun, Earth and moon are in a kind of alignment. All right. So there we go. So I've kind of got the sort of lights here. And then we look at the sort of half moon situation where you've got sort of literally half the moon here. So what you really want is to try and find out the angles of these things. So we know that we want to know r, which is the distance between the sun and the Earth. And obviously, if it's completely blocked, you're not going to see it. But this is when the moon, there is a line between the sun. The Earth, the moon is above the Earth. All right. So there's a line of sight between the sun and the Earth. So you can't really tell that from this 2D picture, but that's the kind of idea. All right. So now what you want to do is you want to sort of like figure out when the half moon is. So if you think that's kind of a bit further round on this on this circle here, but that angle is not 90 degrees there. It's a bit more. All right. And so what you want to do is you want to sort of see, well, you know, it's not a quarter of the lunar period. So if I've got my sort of you know, moon going around the Earth, at the point where we see the half moon, all right, that needs to be a sort of right angled triangle here. That's not quite the same angle. And so what we want to do is that if you, and this is really quite hard to measure. I'm not sure Aristarchus was able to measure this with the clocks they had, but the time of the half moon is 16 minutes 3.1 seconds more than a quarter of your orbital period. So if you kind of look at the picture here, so a quarter of the period was where my sort of dotted blue line would be, but actually where your half moon is going to be here. All right. So we need to sort of work out what that is. Anyway, from that, you do the same calculation and you say, all right, delta t over the period of my moon, all right, is going to be that ratio of angles. So 90 plus theta over 360, all right, is the fraction from where my half moon to new moon is compared to all the way around. So if you rearrange that, what you've got is a very tiny angle of theta. All right, it's about 0.147 degrees. And then once you've got that, you can work out this little tiny triangle. You can use trigonometry to find out what your radius is. So D is the Earth-Moon distance, which we know. So we know that side. And so if D is 60 Earth radii, which we found before, and R sine theta is equal to D, we can then figure out what R is. Of course, Aristarchus wouldn't have known trigonometry either, so he'd have had to have done some Pythagoras or something like this. But we can, you know, we can sort of use a more modern argument, perhaps a clearer argument to work this out. So the sine of 0.147 degrees is quite small, and that's why this is a requires high precision, because we're dividing 60 by a very small number. But anyway, if you get the angle about right, you'll get the Earth-Sun distance, the astronomical unit, which is about 23,386 Earth radii. So there we go. So next time we'll have a look at the speed of light and how we work that one out. But yeah, so far all the distances, the sun, the Earth, and the moon, you can get with good clocks and some careful observation on the Earth, which is pretty cool. So thank you very much indeed. Do come next time, and I will see you then.
Can I stop the recording now, Andy? No extra information? Okay.
No more. I'm just going to smile enthusiastically at you all.